VP of Engineering. Come on up. His company offers the ability to analyze and detect potentially fraudulent reviews, fraudulent transactions, and all kinds of other stuff. And all of this built on AWS using AI. So take it away, David.
Sounds good. Thank you, AWS, for having me. So I'm trying to squeeze about 40 minutes of content into 30 minutes. So we're going to go very fast, but I'll be available after the session in case you have any questions. We could dig into some of the topics in detail. So a little bit about DataVisor. We've been around for about 5 years. We're Series C. About 65% of our company are PhDs from top companies, and we have clients around the world. Some top names from China and some top names here, and you can pretty much recognize some of the logos down at the bottom. So why is fraud important? So you start looking in the news and you start seeing really good companies like Tinder, Instagram, LinkedIn, Apple, Amazon, Airbnb, all have fraud problems. And you say, gosh, I don't want to be the next person having this. So today's content, I'm going to talk about how you can build the stuff, the service yourself, in your group, or you can purchase a service. There's other solutions out there, including DataVisor, but it is a problem where the attackers are using AI to morph the attacks. So if we look at some of the tools traditionally used to block attack, so we can start from the bottom with a reputation list. So you can think of it as a database. Rules engine, firewall is an analogy of rules engine. Supervised machine learning, when you have labels, so a lot of payment transaction e-commerce fraud, use supervised machine learning. And we do a form of machine learning that's complementary to all of these. It's called unsupervised machine learning. So let's cover some of the principles of each of this. So for reputation lists, you can think of it as a database, the simplest form. I will store all of the bad people inside a database. I'll look up every transaction and block the people in my database. Rules engine. They get a little bit more sophisticated because databases, once they find out which ones are blocked, they can actually circumvent it. Then the next natural evolution of that is rules engine, where I can then create rules. And these rules could be sophisticated, where there are things that are positive and negative, and you actually eventually create a score. Using a score threshold, you can tell if a user is good or bad. One of the problems with the rules engine is that it's very manual. It's very hard to keep. You never know how good you are in blocking the attacks, because really good bad guys can actually go under the radar and get through the system against rules engine. Then you evolve to supervised machine learning. With supervised machine learning in its simplest form, like if you look at group A as a good user, group B as a bad user, you take label information, and then in the simplest form, you create a curve to actually divide out the good group versus the bad group. Then you can use label data. It learns on its own. That's why the form machine learning AI come from that. And then as new information comes in, the curve actually automatically adapts. It doesn't have to be linear. It could be, multi-dimensional, and then you can block out attackers that way. Then there's a new form of which is hard to productionize, called unsupervised machine learning, and that's one of the specialty within DataVisor. We use both supervised and unsupervised. Is that what happens is something is unknown when you don't have label data. So it may take you like months before you get label data, and you want to know the attack immediately to stop the damage. So that's basically unsupervised machine learning. The form of it is that you form clusters, intelligent clusters, and you try to utilize the clusters and find out if they're good or bad. So in this chart, go really quickly regarding the pros and cons of each one. We're a little bit tilted toward the unsupervised machine learning because we believe that's the best form of defense against attacks. But in the reputation database, you actually have limited coverage. You don't learn, you can't extrapolate. People can actually reset devices, for example, for mobile application to circumvent it. So blocking IPs, blocking device IDs are not very effective against emulators and device farms. Then the next one is rules engine. I know I maintain firewall myself with lots of rules. It's really hard a human can actually understand about 20 rules with a high level of complexity in your brain. When it goes beyond that, people typically have groups forming portions of the rules. And then it really gets harder and harder. I hear like some of the rules engine have over 10,000 rules. And at that time, it's really hard to comprehend if it is good or bad and how effective you are. In supervised machine learning, A lot of it, basically for chargeback attacks, etc., where you get good labels, you can use that. It's a very effective technique. The issue is that with a lot of the scenario, when you're talking about unknown attack, it's hard to get good label data. So that actually makes it very difficult to use supervised machine learning for all the scenarios. With unsupervised machine learning, you form clusters, and I'll talk in detail exactly how that works. We believe that that's actually the future on how to use AI to block the attacks. So let's actually talk about how we approach it. So I'm going to give you the blueprint to build it yourself. So first of all, you need to really, most of machine learning, the first thing you need to focus on is feature engineering. So we spent many years on going to each different security domain and build thousands of features. And then once you have good features, all these techniques are based on features. Switching algorithms are cheap. Features are really the basis of it. It's pretty much over 90% of the work. You have to think about it, if the attack is real time, where the damage could be real time, you need to basically build features in the real time. And then there's a lot of great frameworks from AWS that provides a basis for you to build these dynamic features. Then the second one is that we actually have our form of unsupervised attack. I'll go through the principle of that. Then once you get the results where you actually have the cluster, we rank them and we look at which ones are the primary form and also extrapolate the reasons behind the attack themselves. So let's talk about a little bit about types of features that you can think about. So there are temporal features. There's event-based, so think about it as sequence. So if you're using a mobile app or a web app, there's natural events that actually happen within the application itself. A lot of the emulation, they're sloppy, so it happens in unnatural sequences, and that actually gives you clues that these are actually not really good forms of usage within the system. Then there's actually velocity and frequency. A lot of the times when you're looking at a certain device level, when there's too much activity from one particular device, from one particular region, one particular city, that actually is suspicious as well. Spatial geo. So one example of what we do on a feature is that we go through all the events and then we find out where the event originates from. So if a person within 5 minutes go from, let's say, Shanghai to Anaheim, it's not possible unless you know how to teleport. So that's actually a really good feature to use to actually capture fraud. And then you have domain attributes. So for each domain, like in the financial industry, internet, telecom industry, there's specific industry-specific domain. So we spend a lot of time with partners to build out the expertise. And then also graph. So there's relational. Like once you know the people, how they're related with each other, you can use that as a way to infer if this is a benevolent group or not, or a malicious group. So essentially from a computational level, once you aggregate all the features, all the data, features is actually the raw data that you collect. You have derived features or things you can compute. Like for a geo or IP address, you can get geo. You could actually get subnet network information. Like for example, one of our features is a person from a data center IP. If they're actually suspicious. 30% of the data center IPs are actually malicious traffic, but 70% are good. So you actually could use these different features to dynamically create a profile. So you have thousands of these. And then after that, you basically form groups, and then it's basically all the possible permutation of all the features. So it is really a large computation. Most of our customers has hundreds of millions of users. One of our customers has over 1 billion users in the system. And then you have to do this within 200 milliseconds, and that's actually the engineering challenge behind that. So some of that, of course, you have to do it offline. So I'll give you one example of what we do offline. So we collect all the IP addresses we know. And what we do is we use our engine to create the label dynamically. So if we know, based on our engine, if it's a bad user, we train our AI and we train our deep learning model based on that so that we can extrapolate all the internet. So we have 25% of the internet, so we understand that from an application behavioral perspective. This is very different from the network. So a lot of times when you talk about IP, it's a network block or edge level detection. We actually focus on application behavior detection. So with this, with about over 4 billion accounts and 800 billion events, we create this database. Ideally, what what the holy grail for us is that we create the deep learning model that actually understand with non-PII information, I can tell you with high confidence if this is a good device, user, or system. So let me give you a concrete example of what this means, because it's a multi-dimensional problem. So in our global intelligence network, as we call it in the product, if you have a Xiaomi M5 phone, it's actually really popular in China, Russia, India. But when it appears in other regions, the crime rate is actually 50% of that traffic is fraudulent. So we can use this information to actually score the group or the user based on this. So with that very simplistic data gathering, you can actually create a very smart, intelligent database based on this. Then with this, when I talked about giving you an example of features, a 1,000 derived feature, we use this to train our model, and then we use that to our detection. So when we tell a customer that we learn attacks from other clients, when there's an attack that happened with client A, client B through Z all learn from it, this is one of the techniques we use to actually learn from the attacks and be able to adapt very quickly. So then, what is really hard is the clustering analysis. So if you look at hundreds of millions of users, and then with all the thousands of attributes, how you're going to basically do the spatial extrapolation, do the clustering very, very quickly, and being able to form the groups based on statistics, et cetera, that's actually what our patent's on, is really fast computation around that, tons of data. More than happy to talk about approach offline, but essentially at a very high level, that's how it works. One of the challenges of AI is that a lot of it, say, for example, deep learning is not explainable. So we spend a lot of time by forming these clusters with all these features, we actually are able to create reasons why these groups are bad. So for example, is this account opening fraud? Is this account taken over? Is it somebody taking a stolen credit card and doing manual transaction fraud? We actually could make it explainable by using these clusters with the features, high priority features, being able to explain the attacks itself. Then, of course, we have UI with analysis. You can dig in and learn more. So over the last 5 years, we actually were able to use this technique to accomplish really high precision, be able to stop fake account creation. So it goes from like credit card application to, or like a mobile app. People will create an account, incubate for a period of time, and then basically attack in a very short period of time, because that's usually, we call it the supercell pattern, where they can actually reap the most damage. It actually defeats supervised machine learning. We also prevent transaction fraud. On the average, we improve it by 30 to 50%. Use this also to identify account takeover, fake reviews and likes, spam, and also fake application installs. So like fake application install, for example, if you buy ads for installs on mobile or the web, about 7.8% of those are fraudulent. So about 10% of your spend actually are going to the hackers. So it's a $7 billion a year industry right now. So give me an example on exactly how this works. And you can see the picture on the right. This is what is a device farm. So all this is done programmatically. It doesn't really need a person to operate. So they actually flash the device, install your application, and fake events within the app itself. So it looks like a real user. So when you go in and you buy this install, what you'll find is that a lot of times people struggle with this. How come is it my app? That's not good? Because people just come in and use it, they never pay, and they never monetize. And then what happened there? And you'll find like 10%, typically a large percentage of those are actually from these device farms. And then you're wasting your good dollars associated with it. So let's actually talk about patterns, because you guys all AWS, you say, gosh, this is a pretty interesting problem. How do you tackle it with cloud technology? So let me go through a couple of things. First of all, I touched deep learning, so I'll touch on it a little bit. So over here, what we do is that we do our feature engineering using Spark. So it is a very good engine, simple API, it's fast. And then the issue is that the integration between deep learning, actually Spark and the deep learning platform that we pick, it's TensorFlow. It's super popular, a lot of momentum around it. Google open sourced it. and it works really well based on our experience. It's production ready, but there's a lot of pitfalls that you'll go through because it's not documented. You'll run into bugs with it. But after you get it to work, it's actually quite good. But one of the big cons of TensorFlow is that we found like the data pre-processing portion of TensorFlow is really poor. So we actually wrote it in Apache Spark. We write the results into a file that gets loaded in TensorFlow, and we train the model in TensorFlow. So really quickly, so if you use Spark, we recommend that you guys use a data frame API. Very easy to learn, very easy to get started, and you can create user feature functions before you train the model. And then behind it, this is a result that we got with about a year of work. So what we found is, like what I said, with all the data we collect, about 25% of the internet, we're able to find that we're able to create a model that extrapolates to the whole internet that beats a lot of the reputation lists that you buy on the market by quite a bit. Especially, there's also feature-specific data lists that you can get. Those are the least effective in terms of being a good feature in your ML model. So for example, there are some reputable vendors doing email domain blacklists or user agent blacklists. Those are fairly ineffective in blocking the attacks. So then the second one is that, as I talked about, like about 90% of the work, over 90% of work is in the feature engineering itself. So I'm going to go through what we do on a pipeline pattern. So we do this on batch level. So we process about 200 gigabytes of data per day per client on the average. And if you calculate QPS, it's about 5,000 QPS if you translate at peak. So it's really high volume. And then so you want this batch process to run multiple times a day. So if you have your real-time system, which we built, we actually use a batch to refresh the model periodically on the batch, from the batch system to make sure that the model is up to date. And then what we did as a strategy is that we dynamically launch and destroy a Spark cluster as a pattern. And we utilize Spot Fleet, and I'll go to detail on why. So this is our cloud trust trend. So if you look at the light blue, it's this year's spend, and the dark blue is last year's spend. So as data volume for our clients grow, so does our spend. As our number of clients increase, our cost actually goes up astronomically. So if you look at the curve here, this actually tells a story. So we actually achieve a 50% reduction within 6 months of work. So what is our strategy? First of all, we're committed to AWS. So we actually went to a 3-year reserved instances model, but we went with a convertible instance because you have the flexibility of switching hardware type. For example, last year we used R3. This year we're using R4. With the same instance around the same price, you actually get way more computational power. So you always want to have the flexibility to upgrade to the latest generation of hardware. Second is that you always need KPIs to optimize costs. So Cloudability has a booth here. We actually picked Cloudability to do our real-time cost tracking for us to, as we optimize, we can see what our cost trajectory looks like, and then as we improve. We also moved to Spot Fleet. So at peak, we run 4,000 instances concurrently inside AWS. So what we found is that bidding in a particular AZ is actually inefficient. So we use Spot Fleet to help us to abstract out like multiple server classes as well as multiple regions. So we're able to bid on those concurrently, and that actually drove down our bid price. So we're able to do that again. We found a cost saving with that. And lastly, we built our own software. It's called SparkGen that did basically the one job or one launch as we talked about. So the curve on the bottom is kind of our trend. The light blue is on demand. So the dark blue is reserved, and then the kind of like the medium blue or the sky blue color is actually our spot usage. This is actually strategically is the right way to go. We went to reserved, which is about 60% cheaper than on demand, and then we went to spot, which is 7 times cheaper than actually on demand. So strategically, you want to increase both of those and basically drive your on demand to 0 if possible. So let's talk a little bit about SparkGen. So as we talk about the strategy, When we thought about it, there's really no good software that we found that actually does the work. Our application actually is quite stateful. So as we learn about a user group, the cluster, that information actually infer good or bad for the future. So it's actually very difficult to basically preserve state. Then on the same time, we want to break down our pipeline to small chunks so that we can maximize parallelization, and also we can actually decrease the cost by actually running the stuff distributed as much as possible. Because some of the jobs are huge, we want to have a huge cluster. Some of the jobs are small, we just want to run a few instances. And then what you want to do is to minimize the amount of time. So this is what we found typically. We talked to a lot of people. They always brag. I'm actually from Yahoo, so I'm going to haze Yahoo for a minute here. We talked about 4,000 servers in a single cluster. We believe that's a horrible strategy. Essentially, you're trying to replicate AWS, so you're trying to avoid that. Utilization using Yarn, et cetera, it's not the optimal if you look at it from a resource utilization perspective. Then you can go in and you divide the cluster and chunk it up to jobs or divisions. We believe that is very manual, and the optimization is not good. So we use a strategy called one job per cluster by dividing this thing to small jobs and launch and then destroying dynamically. So going back to one job per cluster, one of your biggest challenges is actually cutting down launch time. So what we do is we pre-build the AMI. We also do concurrent master-slave initialization. So all of that is done concurrently. And then we actually do it in 2 phases. So what we did was we cut the launch time, if you do it sequentially, from 30 minutes to launch a Spark cluster down to 3 minutes, utilizing this technique. So the last thing I want to talk about is with a stateful application, what you'll need to do is that you actually have the concept of a scheduler that needs to be there. Because what will happen is when you chunk your job into smaller pieces, what you'll find is you have interdependency. And then what you want to do is go from a sequential processing down to concurrent processing. So we built a scheduler to be able to cut down the latency itself, and then being able to understand the dependency between one job to the next. After one job completes, it will actually automatically launch the next one. If it fails, say the spot instance actually is taken away, we actually relaunch that job and rerun that job automatically. So what we're able to achieve is at a peak, we're able to increase the number of executor by 4 times, which is good because we actually cut down the cost by 5x by moving most of our workload onto spot instances, cut the latency, so from beginning to end, by 2x, as well as the cost by 4x. And then this is a chart of our cloud costs, and we're able to reduce the cost by 50%. So I know I covered quite a bit. I'll be available for Q&A after the session as well. So thank you for your time. Just a little bit of advertisement for an engineering group at DataVisor. We're hiring. So if anybody's interested, yes, we could talk afterwards. Thank you very much.